Hey physics folks, welcome to Doc Onco's Physics. Keith Onco here. Today what we want to look at is kinematics in 2 dimensions. We've previously looked at kinematics in 1 dimension, but now we want to take those x and y dimension things that we looked at and put it into 2-dimensional analysis, or otherwise known as projectile motion. Okay, it's not too hard, all right? You just have to follow a process in solving the problems and you'll have great success. Okay. What are some of the keys to understanding how to solve these problems? Well, they're listed over on the left-hand side. These are my keys. One is that we need to recognize that motion in 1 dimension, either x or y, is completely independent of the other dimension. And what do I mean by that? Well, scroll down a little bit here. I've got a funny looking cookie guy over on the left-hand side. And this cookie guy is initially holding 2 peaches. And magically, our cookie guy over here is able to throw one of the peaches out horizontally while dropping another peach vertically at the same exact time. Okay? And if I were to ask you which one is going to hit the ground first, I might get a variety of answers. Some might say peach number 2. Some might say peach number 1. Some might say they're going to both hit the ground at the same time. Well, if I asked you what causes each peach to travel in the downward direction, because they both definitely have downward components to their velocity. This one does, and this one certainly does. They both have downward components to their velocity. What is it that's going to cause the peaches to go in a downward direction? Well, it's the acceleration due to gravity. And that acceleration due to gravity is the same on each of the peaches. So this peach here, number 1, is going to hit the ground at exactly the same time as is peach number 2. Okay? So the fact that the peach number 2 is thrown out horizontally initially makes absolutely no difference when we try and figure out what's going on in the y dimension for that peach versus the x dimension for that peach. Okay? In fact, if we looked at it, when the peach leaves the gingerbread man's hand over here, if peach number 2 leaves the gingerbread man's hand, it has only an x component to its velocity. But quickly, it starts having both an x and a y component, because you can see that while the peach is certainly still traveling in this direction, it's also traveling in the y dimension as well. So it's got both an x component and it's got a y component, and here is the combined components of the velocity going down finally until it hits the ground. So it's got the x component and the y component. Okay? And we're going to analyze those components separately and then finally put them together when we're all done. Okay? But the key in understanding this is knowing that I can analyze my x data and I can analyze my y data separately, all right, and then put them all together. Another key to understanding all this is that the time it takes for peach number 1 to fall is the same exact time it's going to take peach number 2 to fall and hit the ground. They are both going to hit the ground at the exact same time. So if I can find the time that it takes peach number 1 to hit the ground as if I just dropped it, right? So if I just dropped, if the funny looking guy over here just dropped the peach, right, to the ground from the height of his hand, all right, we could find that time. And we would know the total time that the peach was in the air, not just for peach number 1, but also for peach number 2 as well. So we could find out the information for this peach by analyzing what would happen to this peach if we just dropped it. Okay, that may seem a little confusing and you may not even agree with that, but your agreement is not required for it to be the truth. Okay, so keys. The motion in 1 dimension is completely independent of the other dimension. Okay, that's key number 1. Key number 2. I know I've mentioned this before when we do single dimension analysis, right? Analyzing your data All right, collecting information and organizing is a key in the analysis. I have updated the table that we'll be using, and I've got both X dimension data in there and Y dimension data in there. We're going to use both of them. Both of them are required. Okay, you want to keep your information organized. Your accounting is extremely important when it comes to doing these physics problems. Okay, the next one would be analyzing the dimension first that you've got the most data for. Okay, many times this is going to be the Y dimension, all right? And many times it's easier to find the time in the Y dimension, all right, and then apply it to the X dimension. Notice that in our table here, all of our variables have subscripts, right? All of them have subscripts except for time. And the reason time does not have a subscript is that when I find out the time it takes, remember, the time it takes, say, for this peach to hit the ground in situation number 1, that's the same amount of time that the peach is in the air if I throw it horizontally outwards that it's going to take for it to hit the ground. They're both going to hit the ground at the exact same time. And we can use that fact in analyzing our kinematics, right? So the time is the one variable, right, that is going to be the same for each dimension. So once you get time for one of the dimensions, say the Y dimension, you can transfer that over to the X dimension. Or if you found it for the X dimension first, you can transfer it over to the Y dimension. Once you know it on one side, you know it on the other side. All right, so there's 3 basic different types of problems that we're going to look at when we talk about projectile motion. One is, if I've got a playing field over here, I've got a ball over here, and let's say I kick the ball, it goes off, and it lands here. So one of the problems is going to be where my initial Y position, say Y equals 0, is the same as my final Y position, Y equals 0, and I kick the ball, I give it some velocity at some angle. Okay, so that's one type of problem. Another type of problem is going to be where I have a ball or some object up here, and I'm going to shoot it out horizontally. All right, what's going to happen? It's going to follow a path that looks kind of like that. So it's going to fall to the ground eventually, and it's going to follow a path that looks like that. But my initial velocity, my VI, only has an X component here. Over in this case here, my initial velocity has an X component and I have a Y component. Okay, so this is type of problem number 1. This is the problem type number 2. Okay, and problem number 3 is similar to problem number 2, whereas I may have something like this. I'm running out of room here. I'm going to do it in another color. I have an object up here, and instead of firing out horizontally, it's going to fire out a vertical and a horizontal component. So it's going to take a path that looks like this. All right. So it's going to be fired off at some angle with some initial velocity, right? Initial velocity, and it's going to start out at some initial Y position, and it's going to end up at another Y position that is not the same as the initial Y position. Okay, so those are the basic 3 types of projectile motion problems that we're going to be solving. So let's take a look, and we're going to solve one problem in this session, and then what I'm going to do is break up the problem solving for the other types and create a separate YouTube video for each of the different types of problems that we're going to solve. Okay, so let's take a look at this one first. I've got a cannon up at the top of a cliff. This is a classic physics problem. And the initial velocity is going to be 22 meters per second. Okay, now notice that the initial velocity in this problem is in the X dimension only. So I'm going to start filling in my data. So my initial velocity in the X dimension is 22 meters per second. Okay, what's the initial velocity in the Y dimension? Well, it's 0. Okay, I do not have any initial velocity in the Y dimension. Now, once the cannonball leaves the cannon, all right, and that's all we're really interested in here, all right, there's going to be nothing to increase or decrease the velocity of our cannonball. So think about what the definition of acceleration is. It's the change in velocity divided by time, okay? And so if v final and v initial are the same value, my acceleration is going to be 0, because it's going to be 0 divided by some time. So in the x dimension, my velocity for just about all projectile motion problems that we do, my acceleration for just about all projectile motion problems that we're going to do is going to be 0 meters per second squared. Okay? Now, how about our acceleration in the y direction? Well, anytime we have anything going on in the y direction, and there's definitely something going on because this cannonball starts here and it's going to end up at the ground level over here. So what's going to cause it to go to the ground level? Acceleration due to gravity. And so I've already pre-filled in my table. We're assuming we're at the surface of the Earth here. And gravity is going to be negative 9.8 meters per second squared. It's going to be negative because gravity is always pulling down in the negative y direction. Okay? All right, so those are some of the things that I know. What's going to be my initial x position? So this variable right here. Well, I'm going to take what I normally do. Whoops, didn't want to do that. I'm going to take what I normally do, and I'm going to create a coordinate system up there. And this is going to be x equals 0 and y equals 0. So my cannonball starts out at the 0, 0 position. So what can I fill in for my initial x position? 0. My initial y position is 0. Okay. Now, usually I'll also be given the height of our cannon, right? And let's say this is 10 meters in height. Well, if I'm starting out at 0 up here, okay, that means I'm going in the negative y direction when the cannonball finally hits the ground somewhere out here. And so my final y position is going to be the negative 10 meter mark. Okay, so that's the final position in y. My final x position is oftentimes what I'm actually trying to find. All right? The x final position is also sometimes called the range of my projectile. And the range just simply means how far is it going to go in the x direction. Okay, so that's something that we're probably going to be trying to find. In this case, we are trying to find it. Do I know the final velocity in the x direction? Well, if the acceleration is 0, all right, then the final velocity is equal to the initial velocity. That's just 22 meters per second. Okay, so I know that. Do I know the final velocity in the y direction? No, I don't. I do not know what the velocity of the cannonball is going to be just before it hits the ground in that y dimension there. So I can't fill that in yet. Okay, and then finally time. We don't know what the time is. Okay, so these are all the things. So we've filled in our table now with everything that we know. Okay, and so what we're going to do is we're going to start doing some analysis. Well, which is the dimension that I have the most information in? Well, the x dimension, I really only know the initial velocity and the final velocity. I don't know time. I do know the acceleration, and I don't know the final displacement. So I don't have a whole lot there. However, in the y dimension, I know my initial position and my final position. I know my acceleration and my initial velocity. All right, so I can figure out what the time is, all right, using some of the equations. So I'm going to use the same equations here. The key is when I use these equations, I can use them in either the x dimension or the y dimension, but I can't mix up the data. All right, so I can't say I'm going to use this equation right here, all right, and some of my variables are going to be x dimension variables and some are going to be y dimension variables. That does not work. Okay, so I can use this equation for both analysis in the x and the y dimension, but whenever I'm using it, the data that I'm using in the equation has to be just x or just y. All right. In this case, I'm going to look at the y dimension data, and I'm going to try and figure out how much time the cannonball is going to be in the air. Once I know the time on both sides, so that becomes very helpful. Well, let's see. Let's look at equation number 1 here. I know my final position. I know my initial position. So final position, I know the initial position. I know my initial velocity is 0. Okay. I know my acceleration. So I could figure out the time. All right. So my final position is minus 10 meters equals my initial position, which is 0 meters, plus 0 times t, because my initial velocity in the y dimension is 0, plus 1/2 at squared, so negative 9.8 meters per second squared times t squared. Okay, so let's simplify this a little bit. So negative 10 meters is equal to negative 4.9 meters per second squared times t squared. All right. Now, if I divide each side by 4.9 meters per second squared, I can get t squared, and t squared turns out to be about 2.04 seconds squared. So what's t going to be? Well, once I plug that into my calculator, I take the square root of 2.04 seconds, and I get 1.428 seconds. Be careful not to, 1.428 seconds, 1.428 seconds. Don't be careful when it comes to significant digits. You probably didn't need to go, I probably could have rounded this up to 1.43, right? That would have been fine. Don't round down to just 1.4 or 1, because you're going to lose a lot of accuracy, all right? Now, I found the time in the y dimension, and I immediately transferred that over to my time in the x dimension, okay? So now I'd like to know the range, or x final, in the x direction. So this was y information. Now I'm going to be using x information to find out the range. Well, let's look at the information I have on the x side. I know my initial position, all right? I have that. I do not have my final position, which is what I'm looking for. I have initial velocity, final velocity, acceleration, and time, all right? So I'm looking for x final. Well, again, I can use the first equation, right? But now, instead of using the y dimension information, I'm going to have to use the x dimension information. So x final is going to be x initial, which is 0, okay, plus v0 times t. Well, my initial velocity is 22 meters per second, times the time. Well, the time I have now, it's 1.428 seconds, okay, plus 1/2 at squared. Well, 0.5 times a, a is 0. How nice for us. Times t squared, so 1.428 squared, seconds squared, all right? But this whole thing drops out because our acceleration is 0. Makes the calculation really easy. So x final is simply the initial velocity times the time that we calculated, and that turns out to be about 31.4 meters. So that would be the range. That would be how far from the base of our cliff that our projectile would fly in the x dimension. Okay, so what did I do here? I collected all the information that we had from the start, right? I added it to the table. I solved for time because time is one of those key variables that we're going to need on both sides. I had most of the information I needed. I had all the information I needed on the y side. Solved for time, moved that over to the x side, all right? And then I now had enough information to solve the x side information. Okay, so Stay tuned for other problems that I'm going to solve, other projectile motion problems I'm going to solve. I'll put them out there as individual problems so you don't have to listen to this over and over again. I hope that helps, and have a great day.